So I just want to make a couple quick remarks. First thing is Monday is Memorial Day. So we are not, there won't be a lecture, no office hours. Hopefully you can do something fun in this weird time. At least the beaches are open, I guess. I'll probably do a 20-mile hike or something. Make sure that you know, you don't get confused if I'm not around on Monday. I'll be in and out of internet access all weekend. I plan to get out a lot, but I will be checking email here and there. That is my plan. So that's just a note. Second, I want to remind you, just because this is a you know, online-based Eve class, whatever they call it, that doesn't mean you can't get help. It doesn't mean you can't work together. It just means that you have to do it digitally. And I know it's frustrating. It's not the same. It's not the same. Not as good for most people, but it's better than nothing. So let you know, one of the things you can do, for example, you can type in the chat box to a particular person if you wanted to, and invite them to work together. And you can work, you know, via Skype or, you know, whatever internet favorite thing you like to do, which is sometimes better than being by yourself, a little less lonely, I guess. And I'm here to help you out. The tutors are around a lot, okay? So the tutors are around and they're not busy, okay, from what I've heard. So get help from them, and again, you'll make this happen. Because one of the things is, see, this series is hard. So I'll let you know that this class gets harder as it goes. The last couple weeks are really tough. Hopefully, you know, I'm here to help, the tutors are here to help, and hopefully you'll be here to help each other too. So, you know, use each other as assistants and comfort in working together. Also, I want to mention the quizzes that you just took, for example, they're not worth very much in terms of points, but they're worth a lot in terms of practice. So I very strongly recommend you treat the quizzes like the test, because it's very easy to just, you know, pop this on the internet and get the answer. But the problem is in the exam, you can't do that because of Proctorio. So do your best not to just resist the temptation. Resist the temptation while you're taking the quiz to go and look things up. Try and do it without. Try and prep before the quiz. And then when you get to the exam, that will help you, you know, you'll be prepared because then you'll have practiced. Otherwise, all you're doing is another homework assignment. I really try to make the quizzes more like the exams than like the homework. So that's why they're so different, is because they're supposed to be like the exams. And you should do the same for yourself and try to make sure that you're not using all kinds of, you know, internet resources and help. Instead, really just try and sit there, type out the answer. So that's my strong recommendation about the quizzes. They're not, it's just not worth enough points to cheat. There's no reason to. Okay, let me go and share my screen. Let's do this quiz. Okay, so it says for each of the following series, state the name of the type of series that it is, and then determine whether it converges or diverges. Explain why. If it converges, state what it converges to. All right, so let's do part A first. So for part A, we're looking at the summation n equals 0 to infinity of 4 times negative 2 to the n. So the first thing we want to do is see if we can recognize the type of series this is. And what is the name? What is the series called? Yeah, this is a geometric series because it is a form a number times a number to a power. So this is a geometric series. That's the first thing. Okay, so I asked you a few things to do, then determine whether it converges or diverges. Okay, how, with a geometric series, how do you determine if it converges or diverges? What's the...
If the absolute value of r is greater than or less than 1.
Exactly, and in this case, what is r?
-2.
-2, okay? So there's no hard math. You don't need a calculator in any of this stuff, by the way. So we have -2 in absolute value. Maybe I'll even write down just to show it. Absolute value of r is equal to the absolute value of -2. That's what it is. And that's certainly equal to 2. And that is greater than 1. Any questions on that? Okay, and because of that, what's the conclusion?
It diverges.
Yeah. Here's something though, I'm not going to make you do on this quiz, but for now on, you're going to have to do it. Okay, and that is you're going to have to state the test that you're using to show it converges or diverges. In this case, the test is the geometric series test. And abbreviations are great for that, GST. Let me go by GST, the series diverges. So we're going to have like, I don't know, probably 6 or 7 different tests by, in the next week or so. So the geometric series test really is our first test. Okay, it's very easy to use, but you have to know to use it. That's the hard part. Any questions on part A? Okay, let's go to part B. Okay, what kind of series is part B? It's a summation n equals 0 to infinity, 2 over n squared plus 3 minus 2 over n plus 1 squared plus 3. We don't have a comparison test yet, so that's not possible. Yeah, this is a telescoping series. So it's a telescoping series. And those are the only 2 series that we have so far, is we have a geometric series and a telescoping series. So it's not like there's a lot of choices here. It's clearly not a geometric series. What makes it a telescoping series is the difference of consecutive terms. Notice that the difference between these 2 guys is one has an n, the other has an n plus 1. Those are consecutive terms, and if you subtract consecutive terms, then we have a telescoping series. And the nice thing with the telescoping series, then if you want it to converge, what do you have to do? What do you have to check for? There's one thing you have to check. Well, we're going to find Sn eventually, or S infinity, just S. So you have to check that the limit goes to 0. With a telescoping series, you have to make sure the limit as n goes to infinity of the 2 over n squared plus 3 goes to 0. So note that the limit as n approaches infinity of 2 over n squared plus 3 equals 0. Okay, because if it doesn't go to 0, you have no chance. So therefore, the series converges okay, and when you have a telescoping series, an infinite telescoping series, then how do you find out what it converges to? And the hint is it's very easy. Do you remember how telescoping series work? Yeah, you plug in 0. Okay, we plug in 0, so we go 2 divided by parentheses, and I'm just going to write 0 squared plus 3, so you know where it's coming from.
What's up?
And that's equal to 2/3. Any questions on part B? Part C. Okay, what series is this? In 1 word, in 2 words. Yeah, this is a harmonic series.
What?
And what do you know about the harmonic series in terms of convergence or divergence?
It's non-convergent.
Yep,
It's
diverges.
Yeah.
I told you that was the most important one, so of course I'm going to put it on the quiz. Okay, we're going to use it again today, by the way, just let you know. Pretty much every day that ever harmonic series comes up. Okay, any questions on the harmonic series? Okay, so that was easy, I hope, if you recognized it. And let's do part D. What kind of series is part D? Yeah, it's a geometric series. So just like we did before, we need to look at the absolute value of R. What's R in this case? Yeah, R is 1/4. And of course, the absolute value of a fourth is a fourth. And 1/4 is less than 1. Yeah, and in fact, in part A, it's better to say greater than or equal to 1, because that's really what you're testing for. So it's less than 1. So that means it converges. Therefore, by, and let me write down what the harmonic series diverges by the, I'm going to write HST, harmonic series test. Okay, but therefore, by the geometric series test, the series converges. 2, and then there's a formula. Okay, so let's write down the formula. S is equal to, if you remember, it's A naught divided by 1 minus R. And now we just plug in, what's A naught? Yeah, 1/5, so 1/5 divided by 1 minus R, and R we already decided was 1/4. And that's what, a fifth? Let's write it out, 1/5 divided by 1 minus a fourth is 3/4. And then I'm assuming you know how to do fraction arithmetic. So multiply the reciprocal and you get 4/15. Any questions? Any questions on this quiz?
Can you scroll down a little bit?
What's that?
Can you scroll down just a little bit?
Yeah. You mean up, right? Yeah, like that. Yeah, sorry. One of the problems is that for some reason, I see it on my screen and it shows that you're supposed to be seeing it, and I know you're not. Not just you, but everyone. So you have to remind me sometimes to scroll. My computer tricks me. Okay, any questions at all on any of these parts? All right, I want to re-emphasize again a few things. One is for now on, which means starting on Wednesday's quiz, there's no quiz on Monday, of course, you must state the theorem you're using, okay? So I decided I wasn't gonna make you do it today because I hadn't told you yet, and we hadn't had a quiz where, here's an example of doing it, but now you've had examples, and you're gonna have to state the theorems. And by the way, pretty soon you're gonna have like 3 different theorems you have to use in combination to get a convergence. Okay, right now it's just 1, but that'll change. And so you have to state the theorem and show your work. Showing your work is always true, but the stating the theorem and abbreviations are fine. You don't have to, if you want to write geometric series test, you can, but GST is a lot easier. So any questions at all on the quiz? Any questions? Okay, if there's no questions, let's start talking about other tests. So just to let you know, the geometric series test and the telescoping series test have very nice results in that if it converges, you actually get more than just that it converges. You can compute and you can find out what the answer is. Okay. And let you know, that's it. Okay, that's the end of finding the answer. After that, we're not going to be able to find the answer, except in the next chapter towards the end of class. There'll be some that you're actually going to recognize as some interesting function like e to the x or something. But that's another day. But for now, we're done with being able to say, haha, not only does it converge, but I was able to plug in and here's what I got. And this is what it converges. So typically it's not going to be so nice. You're not going to be able to plug in and get an answer. But in a way, for you guys, that's much nicer. How come? Any thoughts? I don't see anyone jumping in. Okay, the answer is if you can't do it, I can't ask you to do it. So it means you have less work to do. Okay, you just have to tell me it converges. Okay, and then you're done. Put a smile face or something, and that's it. You're finished. So this is the end of finding out what it converges to. Now you're just going to have to decide, does it converge or diverge? And then in the deciding, you have to share your work by saying what test you're using. So let's go ahead and we're going to start with the next test. And that's going to be called the divergence test. And I want to emphasize, and I'll re-emphasize and re-emphasize this, is that the result of this is either going to be it diverges or I know nothing. Okay, it's never going to be it converges. So that's a big note with the divergence test, is it's only going to have one answer, and we'll talk about that now. Okay, so the first thing, let me just do an example or two. What if I told you, let's look at the sum, just for fun. That one, there we go. So it's a sum. And just note, I think I'm gonna not put in anything on top and bottom. If I don't put anything top and bottom, it just means we're going off to infinity, and it doesn't matter what you start at. For divergence and convergence, it's only the tail that matters. So just for now on, if I just write sigma, that just means n is going to go from some number up to infinity. It just means less writing. And you can get away with that for now on because we're not going to compute anything. We're just going to decide whether it converges or diverges. So who cares where it starts? Okay, and it's always going to end at infinity for pretty much the rest of this class. Okay, except one section. So let's suppose we have the summation of 2. Can you tell me about that sum? Converges or diverges? What do you think? Yeah, why do you think it diverges? Yeah, it's constant. If you go 2 plus 2 plus 2 plus 2 plus 2, it's just going to get bigger and bigger and bigger and bigger and bigger and bigger and bigger, right? What's the only way for any series for it not to keep getting bigger all the time? Because adding 2 over and over again didn't work. And by the way, same thing with 3. What's the only way for it not to keep getting bigger and bigger and bigger? Can divide? Yeah, there's funky ways of not having it divide, even though it looks like it's kind of like dividing. Dividing is one way, but not the only way. Yeah, subtraction, again, you're talking about getting things smaller or whatever. But the idea is, if we're going to be adding forever, and that's what we're talking about, and adding and subtracting is fine, then at the end, we better not be adding by much. Is that clear? And that's what this divergence test is going to be about, is that if you keep adding by a significant amount forever, it's never going to converge. Another example, let's write this in. So I should write diverges. Let me give you another example that diverges. I think I can do it this way. Let's see. There it is. Yeah. So another example that diverges is a summation of, whoa, that's not what I meant to do. There we go. I think it did Control A by mistake or something. Summation of -1 to the n. Why does that diverge? Yeah, why does that one diverge? The rate is 1. Yeah, but just think about what's going on with it. Yeah, it's gonna switch from 1 to 0. Okay. So the idea here is that we're going to start with n equals 0, then you get 1. Then you're going to add -1, you get 0. Then you're going to add 1, you get a 1. Then you're going to add -1, you get a 0. And it's going to pop up and down from 1 to 0 to 1 to 0 to 1 to 0 to 1 to 0. And converges means that it eventually stabilizes and becomes the same number. Does that make sense? The only way you're going to stabilize and become the same number as you add is if you're adding 0 or things that are very, very close to 0. Because as soon as you're not adding 0, that means you're changing the number. So that is the idea of this big theorem. And this theorem is called the divergence test. And it says, let me make that red. So let the summation of an be such that the limit as n approaches infinity of a sub n is not equal to 0. Then the series diverges. So again, if we have a sum, like the summation of 2, the limit goes to 2. Or the summation of -1 to the n, that limit doesn't exist, right? The limit as n goes to infinity does not exist for -1 to the n because it oscillates up and down and up and down and up and down. Okay, so if it doesn't exist or if it's not 0, I mean, if it's not 0, which means it doesn't exist or is some non-zero number, then we can say the series diverges. Any questions on the theorem? Okay, does that mean that if it does go to 0, the series converges? If the limit goes to 0, does it mean the series converges? Now, can you come up with an example? Here's a hint, it's the example. Yeah,
Harmonic.
exactly. The harmonic series is an example of a series where an does go to 0. 1 over n definitely goes to 0 as n goes to infinity. but the summation goes to infinity. It doesn't go to zero. It doesn't converge. Okay, so that's why this is called the divergence test, because it only tells you, the only two results are it diverges or I don't know. Okay, any questions on this test? Okay, the proof is actually kind of easy, so I figure I might as well do it. And it kind of demonstrates something. And that is that imagine we have a summation. We have the summation of AN. And let's say you start adding it up. And I'm going to add it up also. We're both going to add it up. Okay? But you're going to start earlier than I am. You're going to start one earlier than I am. So you're going to have A1 done before, and you're going to have A1 done before I start. When you're on A2, I'm going to be on A1. Okay? When you're on E3, I'm going to be on A2. Is that clear? When we're finished, if it were to converge, we should have the same answer, right? Is that clear? That's what convergence means, is if you go to the, trillionth one versus trillion and first one, you're very close to the same answer, and in the limit, you are the same answer. So if we look at Sn, that would be yours, minus S sub n minus 1. That's mine. I'm one behind y'all. Then that should converge to 0. Because even if I'm one behind you, if we both go off to infinity, we're gonna be, way out there at the same place. So that is going to converge to 0. Because if we subtract our two answers way out there, we're going to have the same answer. Any questions on that? Okay, but what is Sn minus 1? The hint is it's pretty easy. So what's Sn minus 1? Okay, think about it. If you're on the 100th one, I'm on the 99th one, and we subtract our sums, what's left? If you'd add up the first 100 of them, I've added up the first 99, and we subtract them, what do we get? We get the, not one, we get the 100th one. Because I've only added up to 99, I take mine away from your 100, and now we're left with the 100th one. Do you see that? Because I've taken all my lower ones away. This is actually A sub n. And that's the whole proof. So that means A sub n better go to 0 if it converges. I guess I should write if it converges, then we know that must be true. So therefore, the limit A sub n goes to 0, which means that if it doesn't go to 0, it doesn't converge. Any questions on that? So it's a simple proof if you understand it. Okay, so it's pretty easy to use. That's the good news. So let's do some examples. How about what if we looked at the sum of a fraction? And let's suppose we looked at n squared plus 2n minus 3. divided by 4n squared plus 7. What can you say about that series in terms of convergence or divergence? What can you say about this series? Does it converge or does it diverge? Again, it's a little messier, but it shouldn't be hard. That's a hint. You're all being quiet. Hopefully it means you still hear me. So does this converge or diverge? Yeah, this one diverges. And let's see why. Okay. So what we want to do is want to use this divergence test. That's probably obvious that that's what we need to do, but it's always a good try. And you could usually just visualize it and see that that's a good test to use. Okay. So let's go and, oh, actually, let's do this. I don't have to retype it. Let's take the limit as n goes to infinity. Of this guy. Make it bigger so we can see it. Oh, it's that one. There we go. Okay, how do we take that limit? Any idea?
We simplify it algebraically. Oh, no, it's L'Hopital's rule.
Yeah, L'Hopital. Might as well say it in French. L'Hopital's rule. Okay, so this is equal to, I'm just going to copy and paste and then do L'Hopital's rule. So we the limit as n goes to infinity. We take the derivative of the top, and that's going to be 2n plus 2 over 8n over 8n. And then take L'Hopital's rule one more time, because we still get infinity over infinity. That means we can keep doing L'Hopital's rule. Okay, it was a requirement in my PhD to take French, by the way. French and Russian, and I had already taken Spanish, Hebrew, and Japanese. So a lot of languages.
Are you still fluent in all of them?
No.
No.
I know a little here and there though. I knew them all once, so. Okay, yeah, my brain can't handle that many languages at once. Okay, so again, derivative of 8n is 8. Derivative of 2n plus 2 is 2. And now this is very easy. You better all know, what is this limit? This is supposed to be easy. Yeah, 1/4. And by the way, the important thing, all that really matters is that 1/4 is not equal to 0. And you all know that. So therefore, by the divergence test, the series diverges. Any questions on that?
Isn't there something that talks, I forget where I know this from, where it's like if the limit, within the limit, if you have like two polynomials over each other, it's, and the degrees, the leading coefficients are the same. It like,
Yeah, that's
Yeah,
it approaches-
that's a theorem that comes from L'Hopital's rule.
okay.
So it also comes from algebra. There's two ways of proving it. I figure I mean, look, this wasn't hard, was it? I mean, those are easy derivatives. So I figure I might as well just do it to remind you of L'Hopital's rule because it does come up. Okay, any questions at all on using it? Let me do another example. Let me copy and paste this and change it. And to make it a lot simpler. What if we have the summation of 1 over n squared? What does the divergence theorem tell us? With this one. And we'll let n start at 1, by the way, on this one. Maybe I'll even make it n plus 1, so then I don't have to worry about it. There, then n can start at 0. What does the divergence theorem tell us? Not seeing y'all jumping. Maybe I should state it. The divergence theorem, we don't need it so big now. The divergence theorem does not tell us anything, does not give us any information about this series. How come? Yeah, the limit is equal to 0, so the divergence theorem fails. So do you think this converges or diverges? What's your guess? Any guess?
I think it converges.
Yeah, and we're going to be able to prove it. The harder question is, what does it converge to?
Not sure.
Right? Right? What is, 1 plus 1/4 plus 1/9 plus 1/16, all the way up. Okay, I'm sure you are all thinking about pi squared over 6. So, you could just admit that you were thinking that. But it does converge, and that's what it converges to. And that, the pi squared over 6 idea, that we're not going to be able to understand for many weeks. I think that might be the last week of class. Okay, the last week of lecture is to understand that that's actually equal to pi squared over 6. But we're not ready for that, not even close. Okay, but I will tell you it's going to converge, and by the end of today, which is not that much time, we'll actually be able to figure out why. Any questions at all on the divergence test? Using it and knowing when not to use it. So the second example is a don't use it, because all you get is we know nothing, and that doesn't tell you anything. It doesn't mean you can't figure it out, because I told you, I figured it out. We're going to figure this out later, not with, you just can't figure it out with the divergence test. We're going to need a different test. Any questions at all so far before we move on to the next test? Okay, so let's go on to the next test. And what I want you to think about is last quarter, okay? We don't do a whole lot from last quarter in this class, but this is the one time we're going to. And that is, what was last quarter all about? Your memories aren't that bad, I hope. In one word,
Integration.
yeah, integration, okay? And integration, by definition, is a series. Is that clear? Because we defined integration, if you remember, as a summation of f of I plus, if you remember, there was a summation of the areas of the rectangles. Do you remember that? I want to do a little review on integration. So do you remember this picture? Okay, and I want to show you two things. If we look at the area shaded in light blue over here, those are right rectangles. Do you agree? Any questions on that? Okay, on the other hand, if you look at the area that includes the higher rectangles, those are left rectangles. Is that clear?
Yeah.
Okay, so one of the things we know for sure is that if we look at the right rectangles, if you have a decreasing function of x, then the right rectangles are always going to be less than the integral. Is that clear? If you have a decreasing positive function of x, then the right rectangles are going to be less than the integral. Any questions on that? Okay. On the other hand, the left rectangles are going to be more than the integral. Is that clear? But there's another way of thinking about left and right rectangles. If you compare them, notice that the first left rectangle here, the first right rectangle, that's this guy, it has the same area as the second left rectangle. So this rectangle, this tall rectangle here, it has the same area as the shorter rectangle just to the left of it. Any questions on that picture? And you could keep doing this forever. So if I go over to this rectangle in between 5 and 6, that rectangle will have the same area as the taller rectangle between 6 and 7. So if we add up the rectangles, whether you're adding up the lower rectangle, the right rectangles, or you add up the left rectangles, whether it converges or diverges will be the same. Is that clear? Because all that matters is whether you're including that first rectangle or not. Any questions on the picture? So we've talked about integration, and we know how to tell if an integral converges or diverges. You integrate it, take a limit, and if you get infinity, then it diverged. And if you don't get infinity, then it converged. Is that clear? But what we see is that because the series is, in a way, both above and below the integral, depending on whether you're counting the first rectangle or not, the convergence of the integral is exactly the same as the convergence of the series. So if the series converges, if the integral converges, then the series converges. And if the integral diverges, the series will diverge. Right? If you integrate and you get an infinite amount of area, well, then the sum of these rectangles must have been infinite, because these lower rectangles are smaller than the area. So, the higher rectangles are bigger. So if you got an infinite number for the smaller number, well, then the bigger number is clearly infinity. And similarly, if you get a finite number for the integral, then we could look at these lower rectangles. And well, if the area total converges and it's bigger than the summation of all these rectangles area, then the summation of the rectangles area must converge. Any questions at all on this idea? Okay, I like this because it's very visual if you understood what I just said. Anyone lost? Okay, so now I'm going to state what I just said as the big theorem. And this theorem is called the integral test. For hopefully to you guys obvious reasons. And it says the following. Okay, so let f of n equal a sub n. So suppose we have a integrable function such that it agrees with a sub n at the integers. Okay. And all we really need is for large n. It doesn't matter for the first 10. All that matters is the tail anyway. So for large n. And suppose that we need two things. One is we need a sub n to be greater than or equal to 0. Let me get that, greater than or equal to. Okay, we don't want to go below the x-axis. All hell breaks loose if you do that. And we need to make sure that we have a decreasing sequence. I think I'll write down in the A's, but I'll also mention in the F's. And a sub n plus 1 is less than, well, less than or equal to, well, actually less than a sub n, or all large n. Okay. In terms of the f's, that means same thing is that f of n plus 1 is less than f of n. For a function, how do you determine that inequality? What's the easy way from first quarter calculus? Who remembers how to do that? I know it's been a lot of months, but everything comes back. So how do you determine that you keep going down for a function? No one knows? I need to talk to Bruce if you don't know. Right? It's decreasing if the derivative is negative. Do you remember that?
Oh, yeah, yeah.
That was a biggie in the first quarter calculus, wasn't it? Decreasing means the first derivative is negative. Okay, so if the first derivative is negative, then you're in good shape. Okay, so sometimes it's easier to show the first derivative is negative. Sometimes it's easier to show that an plus 1 is less than an. It all depends on the situation. Okay, then now we need to write down the integral from 0 to infinity. That one. Of f of x dx converges if and only if the summation of a sub n converges. Okay, so just a note, if and only if means that if the integral converges, then the series converges. It also means that if the integral diverges, the series diverges. When you have the and only if, that means you can go either direction. So if the right is not true, the left must not have been true, and vice versa. So convergence and divergence are here. Okay, what you see for the integral is the same as what you see for the series. And I should write down the integral function. Integral. Okay, oops. Okay, if you can't take an integral, then this theorem is useless. Do y'all agree? Okay, so most functions you deal with are integrable, except not in this class. And we'll see that in a bit. We have all kinds of problems. We're not going to be able to find an f. Okay, or let's just put it this way. You're not going to know how to find an f. Any questions on the theorem before we do some examples? Okay, the proof is by picture. And then if what I said verbally, if I had typed it all out, that's the proof. Okay, all you do is you look at the summation of an, you look at it in two different ways. You kind of ignore the first rectangle versus not ignoring the first rectangle. And you can say that the integral is always bounded in between by ignoring and not ignoring, but convergence and divergence have nothing to do with the first rectangle. All that matters is all the last billion of them, you know, and trillion and, you know, et cetera, et cetera. So that's all that does. So that says that if one goes to infinity, the other must have gone to infinity from the inequalities I said a little while ago. So I kind of said the proof, even though I didn't write it out. But you can find it in the book. Any questions on this big theorem? Okay, this theorem is useful. So let's do some examples. All right, let me do the one we were just talking about. And that was the summation. In fact, I think I wrote it down over here. So I can just copy and paste. And just to make life easier, we'll start at 1 and call it 1 over n squared. Okay, and this is n equals 1 to infinity now. So we don't have any issues with plugging in 0. How do I decide if this converges or diverges? We already decided you can't use the divergence test. So what test do you think I might use? Not a trick question. It's supposed to be easy. What test do you think I'm going to use to decide if it converges? Yeah, this is the integral test. Okay. Here's another really easy question. What function f of x will give me 1 over n squared when you plug it in? The hint is very easy. What function should I use? Yeah, x to the negative 2 or 1 over x squared. I'm going to write it as 1 over x squared because it just looks like the 1. It's going to be 1 over x squared. All right. Well, first thing, I'll put it within because it's so easy. That's certainly greater than 0. Do y'all agree? Okay, and when we're saying greater than 0, we mean for n large. Okay, or for x large. For large numbers, 1 over x squared is definitely positive. No problems with negative numbers. Is this an increasing or decreasing function? How do I find out? How do I decide whether it's a decreasing function? Any ideas? Yeah, we take the derivative. So f prime of x is equal to, well, the derivative of x to the negative 2 is negative 2 times x to the negative 3. And remember, we're talking about large x. X is positive in particular. This is certainly less than 0. So it is decreasing. Okay, so that means that we now have a function that is in the right form to be able to use the integral test. So what we want to do is we're going to integrate. And when I said, maybe I'm going to change the 0 to an a, it doesn't matter, just any positive a for a large. Maybe I'll make that look like a symbol. Okay, as long as a is large, that's what we care about. So again, don't worry about plugging 0 because we're not anyway. So now let's take an integral. Let's take an integral. And I think something needs to. There we go. Let's take an integral. And let's do that. So we're going to have an integral. I'll just let a be large. How about 1? Sound good enough? That's large enough for all I need. I just want to make sure it's not 0. To infinity of 1 over x squared. Dx. All right. You better know how to do this, or maybe I need to change your grade from last quarter. How do you integrate 1 over x squared? Don't give me a logarithm, please.
Negative 1 over x.
Yeah. So that's going to be negative 1 over x. And then from 1 to infinity. And I'm going to be a little lazy. I'm going to write 1 to infinity instead of limit as n goes to infinity, all that. We're just going to put that all together. And is that defined? What's 1 over infinity? Yeah, 1 over infinity is 0. So I'm going to write 0. That's going to be 0 plus 1 equal 1. Okay, now do you remember if we take an improper integral and we get a number, what can we say? In one word.
Sorry
One
about
word.
that. That was my sister.
Yeah, converges. Therefore, the integral converges. So by the integral test, the series converges. Notice that this does not in any way tell us exactly what it converges to. Okay, all it does is say it converges. Okay, we need more advanced stuff to understand what it converges to, but you could like use a computer, let it go to 1,000,000 or so, and there's a good chance that that'll be pretty good. Any questions on that? Okay, now let me take this example that we just did and generalize and do one more before I generalize it. How about 1 over n? We've seen that one before, right? N equals 1 to infinity. And we can do the same thing. In this case, f of x is equal to 1 over x. And I think I'm just going to say it. 1 over x is positive for large x, and 1 over x is decreasing, right? The derivative is negative 1 over x squared. That's a negative number for all x, actually. Okay, all positive x. So it is decreasing and positive. So that means we can do the integral test. So let's do the integral test. So we're going to take the integral from 1 to infinity of 1 over x dx. You better all know how to do that integral. What's the integral of 1 over x dx? From 1 to infinity, so don't worry about negatives. All right, what's the integral of 1 over x? Yeah, natural log of the x. Normally absolute value, but you don't need absolute value since x is positive. So natural log of x. And again, that's from 1 to infinity. What's natural log of infinity? Yeah, natural log of infinity is infinity, so it diverges. Therefore, another proof that the harmonic series diverges. We don't need to be so big. Any questions on this? Okay, let's do the example of all of these. There's a very important example. That is, what if we had 1 over n to the p. Okay, p stands for power, by the way. Okay, so we can do exactly the same thing. Is notice that f of x is equal to 1 over x to the p. That's no problem. And I'm just going to copy a lot of this. Certainly, it's decreasing in positive. Okay, do y'all agree for positive x? And we could do the integral of 1 over x to the p. Okay, remember 1 over x to the p is the same as x to the negative p. And the integral of x to the negative p now is, well, that's going to be x to the negative p plus 1 divided by p plus 1. So that's 1 over p, negative p plus 1 times x to the negative p plus 1. From 1 to infinity. Anyone lost on this? Is that okay? So now the big question is, if I plug in infinity, when do I get that first case where it went to 0, and when do I get the next case where it went to infinity? Any thoughts? So I'm going to write, oops, converges for, and now I want the inequality. For what values of p will this converge? Yeah, p greater than 1. Right, p equal 1, we already had a problem. And this doesn't even work for p equal 1. This is harmonic, and you can't use the power rule like that. But if p is less than 1, then you diverge. If p is greater than 1, you converge. And diverges for p less than 1. Well, by the integral test, make it capital. And if you want, you can call that IT, not information technology, by the way. We can conclude that summation of 1 over n to the p converges for p greater than 1. And we can write the same thing, but switch it around. The summation of 1 over n to the p diverges for p less than or equal to 1. Okay, and I'm going to give this a name. There's a theorem, even though it's a corollary of this integral test, but it's a theorem. and it's called the P-series test. It's so important it needs its own name. So it happens so many times, you don't want to have to do the integral test every time. All you have to do is look at the power and see whether it's greater than 1 or not. If it's greater than 1, you say converges by the P-series test. If it is less than or equal to 1, it diverges by the P-series test. Any questions at all on okay. Then finally, because we got a little time left, one of the things you want to do is your first step typically in engineering or whatever you're doing is to say, does it converge? If it diverges, you give up. Does that make sense? If it converges, what is the next thing you might be interested in? Almost certainly you're going to be interested in. The hint is you had to do it on the quiz today. So if it converges, what will you be interested in?
Value it converges to.
Yeah, what does it converge to? And I told you the bad news. The bad news is for most examples, you're never going to know. The good news is if it converges, that means that if you go for a long way, you're going to be close. You're never going to get exactly there, but you can be close. It's like if I ask you exactly what is pi, could you tell me? Right, no way, no way. 3.1415926. Eventually you're going to forget and you're not going to know what happens after. Okay, most of you better know 2 decimal places, but eventually you're not going to know the rest. Okay, believe it or not, pi can be defined as a series. Remember pi squared over 6? You just multiply that by 6 and you go 6 over n squared. That's pi. And you want to be able to approximate pi using that series. And you can't get it exactly. You're never going to get exactly, but you can get it approximately. So you can go 1,000,000 times and you'll be close. Does that make sense? So the idea here is the following. And it comes from this picture yet again. This picture is great. And that what we do know is that the integral is strapped between not counting the first term and counting the first term. You see that? So the integral is going to be less than counting the first term. And it's going to be more than starting at the second term. And that's because of left and right rectangles. Okay, well, that pretty much tells us that if we go up to 1,000 terms, we don't have to just say the first term. But if we just go up to 1,000 terms, well, we can use the integral as an approximation of what's left. Any questions on that idea before I state the theorem? Any questions? Okay, so note, let me define something. We have a few minutes left, just in time. Rn, I use capital N, so I'm going to use capital N also. Be equal to S minus Sn. So a lot of symbols here. We've had most of them. Remember, S represents the sum, the infinite sum of the series. Sn means stop at the nth term. So add them up, but stop at the nth term. So if you use adding all the way up to the nth term as your approximation, then your S minus Sn will be the remainder, kind of your error term. Does that make sense? And the theorem is the following. And that is that Rn will always be between the integrals. So let me write that out. So integral starting at n plus 1 and going to infinity of the f of x dx, where, by the way, I'm not going to write it out, but f of n is an. So today, that's always true when you have a function you're integrating. It means that we're using it as our approximation. That is going to be less than or equal to the summation. Sorry, not summation, just Rn. There's summation, but it's in there. Which is less than or equal to basically the same thing, but not starting at n plus 1. Starting at n. So if we do an approximation by adding up the first 100 terms, for example, well, we can integrate from 100 to infinity, and that'll be an upper bound for our error, our remainder. We can integrate from 101 to infinity, and that'll be a lower bound for the error. Any questions on this? Okay. Notice that if it diverges, the error is infinite. That's what divergence means. Okay. So again, if you say 1 over n squared, you can actually do that and say, well, let's say you wanted to add up the first 100 ones, all the way up to 1 over 10,000 squared. I mean, sorry, 10,000, 1 over 100 squared. And you want to see how good an approximation is that. Well, we integrate. So let's integrate. From 100 to infinity. And just for fun, I'll put the 6 on top. You multiply by 6, you get pi is the idea when you have 1 over n squared. So let's go fraction. 6 over n squared. Six over, whoops, x squared dx. All right, and the idea when you integrate that, you get negative 6 over x, right? And infinity gives you 0, 100 gives you 6 over 100, which is 0.06. So that means that if you want to approximate pi by adding up the first 100 square reciprocals, you'll be off by no more than 0.06. Any questions on that idea? Okay, I am looking at my clock and it is 10:15 exactly. So I'm going to stop the recording.